Hi, everybody. I should probably start off with an apology in the sense that after the opening session this afternoon, Sam and I were talking, and I realized I actually never introduced myself, maybe quite arrogantly there. I'm Shiv. You've gotten a lot of emails from me. I apologize for that. But anyway, let's get that out of the sort of... we are here to listen to our first plenary speaker, Dr. Keene. And to introduce her, I'm going to introduce Dr. Chris Rasmussen. Both of them are virtual, as you can see, in keeping with our theme for the conference. Chris will go first and introduce Karen, and then, if everything goes according to plan, Karen will take over. Chris, to you.
Thanks, Shiv. And the first day of the conference is going very well. So congratulations, Shiv, for pulling this off. So it's a big pleasure and honor to introduce my friend and colleague, Dr. Karen Allen Keene, for the kickoff plenary of RUME 2022. We both wish we could be there in person, but thanks for organizing a virtual opportunity. Many of you know Karen as our current Sigma on RUME organizational director and longstanding exceptional RUME scholar. You may not know, however, that Karen was a high school teacher for 20 years, which may explain why she's so amazingly grounded and able to deal with all of my childish behavior. Karen received her bachelor's and master's degree in mathematics from Butler University and her PhD in mathematics education from Purdue University. She is currently chair of the Department of STEM Education at Embry-Riddle Aeronautical University. And prior to taking on this position, Karen was a program officer in NSF's Division of Undergraduate Education and Human Resources Directorate. Before that, she was a professor at NC State for, I think, about 6.5, 7 years, something like that. Karen's research interests span the teaching and learning of differential equations, professional development, the social construction of mathematical meaning, how teachers' content knowledge connects to their teaching, and curriculum development. I've had the pleasure of knowing Karen since, gosh, I don't know, 1998, 99, something like that, when I was as green as they come, fresh out of my own PhD program. And somehow I had the good fortune of Karen wanting to work with me for her dissertation. So that was a real privilege and honor. And we've been working together ever since that time. We're co-authors on the inquiry-oriented differential equations curriculum and continue to co-author papers. We recently published a paper in JMB on waypoints in differential equations, rates of change, something that we've been thinking about for 10 plus years. We finally got around to writing it. And we're continuing scheming sort of new grants we want to put together. So it's a wonderful, long-lasting friendship and partnership. Some fun personal facts about Karen. She's an extraordinary pianist, and she can drive a mean speedboat. If you get in the boat with her, you got to hold on. She will take that boat around that lake. If you ever have a chance to sit down, you should with Karen and chat. She's one of the smartest people in RUME, and without a doubt, one of the kindest and nicest people you will meet in this community. So please join me in welcoming Dr. Karen Allen Keene. With that, I turn it over to you, Karen.
Okay, I'm going to share my screen, I believe. Okay. Can you all see it? Did somebody unmute themselves and say if they can see it or not? Oh,
I cannot see your screen.
You're not seeing my, okay, let's try this.
Now I can see your screen.
Okay, thank you. Okay, I guess here we go. We didn't know how everything was going to work out, and it's a crazy time, that's for sure. I want to thank all of you for coming, and thank you, Chris, for that very nice introduction. I'm a little bit worried because when I go to the lake house, I'm afraid I'm going to have about 200 people want to come and take a ride in my speedboat. So if you're going to come, give me a heads up, and I'll be sure there's gas in it, because that's kind of one of my favorite places to be, is out on a lake in a boat. But the other favorite place I guess I have to be is right here where I am at. So I'm going to give some of this history Chris briefly mentioned, so I'll kind of go through it. But let me see if I can get this. Yeah. So I want to thank you for the opportunity to speak. It's my privilege. It's my honor. I really wanted to be there in person, and I'm sorry that I'm not, but know that my heart is certainly up there in Boston with all of you, as you are getting to be a part of one of the most amazing groups of researchers that I've ever think it could possibly exist. This is what my talk is going to look like. I'm going to try to talk about 45 minutes, and then there'll be time for some questions. Or I remember these first nights when everybody is tired from having flown in. So if we get done before early, I think that's fine too. Or if you're all waiting to get out there and catch up with each other. So I'm going to talk a little bit about my background and where I came from. And then I'm going to talk about the emergent perspective. I'm going to talk about differential equations, supporting instructors, and online. So of course, as you look at this, you can kind of hear what Chris was talking about. I've kind of had a wide variety over the 20 years I've been working in RUME, but I'm going to try to tie it all together tonight. And so hopefully that will give you some sense of where it is. Whoever is manning this chat, I do not have the chat up. Is it Shiv you are, I think? So whoever's manning the chat, you'll have to tell me if there's a question that comes before the end of the talk, because I'll need to talk about it. So I thought you'd like to see, I'm sure you couldn't guess this from looking at me, but I've been around a long time doing mathematics. I taught high school. I taught undergraduate mathematics in a small department or a small college in Northwest Indiana. And then in 2006, I finished my PhD. So I'm one of those people that didn't know exactly where they were going to go when they started, I guess. I always wanted to be a high school teacher, and I loved teaching high school. But then I found out that I really wanted to dig deeper into the learning of mathematics. I guess that's what it was about. And so I was teaching at a small school next door to Notre Dame. So I first looked into going to Notre Dame and becoming a mathematician. And that was interesting. I thought that was good. But the more I thought about it, I thought not so interested in the mathematics as I am in the students and how the students learn and how the teachers teach. So I found Purdue, and I found an advisor in Dr. Rasmussen, as he's already said. And during the years that I was teaching at Valparaiso University, I did my PhD and finished in 2006. So at that point, I became fairly passionate about studying how we can best learn about how students learn at the college level. And so that's the emergence perspective. I'll be speaking about this tonight. Took a little break for 3 years and worked at the National Science Foundation. I'm sure several of you have seen my name on different things. I'm not going to talk about my work at the National Science Foundation tonight. That was because that was kind of a 3 years away from, and I didn't get to do as much research as I wanted, and now back. And so right now I started at a university that's called Embry-Riddle Aeronautical University, which you may or may not have heard of. And at Embry-Riddle, I'm the department chair for the STEM education department in an completely online setting. So I'm going to talk a little bit about what that might mean for us now. 10 years ago, we would have said, we don't really need to worry about that because it's not going to ever be all online. But as you know, that didn't happen. And so I think this becomes more and more important as time goes on. So that's kind of what the talk is going to be about. Some areas will be a little bit more fleshed out than others, but I'm trying to put together an overarching theme. So I want to start by thanking some people. I don't know how, if I was in the room, I'd be asking people if they know who's who of this list down here and these people that are around here. But since I'm not in the room with you, I can't ask you that. Dr. Freudenthal is on the left, top left. Kuno is in the middle. Paul Cobb is on the right. Erna Yekel is on the bottom left. And then Chris, my dissertation advisor and longtime friend and colleague. So these people I had never heard of. When you teach high school, there's not a whole lot of time to think about things like how exactly do students construct meaning, of mathematics, or what does it mean to do mathematics? You don't think a whole lot about it when you have 120 students in 6 classes every day. So I had never heard of or thought of any of these things until I started into my PhD program. And it was life-changing. Particularly Dr. Freudenthal's thoughts about what mathematics is changed the way I thought about learning and about the way I wanted to be a researcher. Dr. Graveimeijer is one of the primaries who developed realistic mathematics education, and I will be speaking a little bit about that. And then Dr. Cobb and Dr. Yackel developed the emergent perspective and the interpretive framework, which I also will be talking about. And Chris is one of the leaders who brought all of these folks' work into the college level. So that's why he gets a picture up there. So I'm going to start with telling you a little bit about the emergent perspective. Again, this was written in 1996. When I started in 2001, 2002, thinking about this, it wasn't that old. Now today it's 25 years old, so it's been around a lot. The emergent perspective says, or this is in my own words, so you may say it in slightly different words, that learning, particularly learning mathematics, can't be just placed in one category. That how students learn mathematics and how we ought to consider it as we decide how to teach it needs to be thought of from both perspectives. So the emergent perspective, then the way that Dr. Cobb and Dr. Yackel chose to use it is by putting together what they call the interpretive framework. So as you notice, on the left is called the social perspective, and on the right is called the individual perspective. And their philosophy or their belief was that that they are reflexive to each other, that you can't have one without the other, and you have to think about both of them. So I'll talk just briefly about each of them. I wanted to give Chris and Megan Walru and Michelle Zandier credit because they slightly revised it and added a little bit more down at the bottom. Because most of my work is primarily focused at the top, I will be using the original framework, but I think that their contribution of adding in disciplinary practices and mathematical meaning is a helpful way to think about it as well. So classroom social norms and social mathematical norms and classroom mathematics practices are all about learning. And it doesn't have to necessarily be in the classroom, I don't think, but learning together with other people. And so classroom social norms would be things like, what is acceptable as an elegant explanation? When should I raise my hand? Is it appropriate to interrupt somebody? Things that set the norms for a classroom. Now, Erna, I'm going to call Dr. Yackel Erna, or Dr. Yackel Erna. Erna's work, on all of their work, involved not the kind of classrooms that we are used to. Like they weren't sitting in, they weren't standing in the front and had a group of people outside of them looking at that. It was not like that. The students were working and putting together their ideas at once, and I'll talk a little bit more about that in a minute. So the social side was things that would happen because students were learning mathematics together. I still to this day, and it's been 20 years now, struggle with some of the definitions like classroom mathematics practices. But that classroom mathematics practices is what is taken as shared in a classroom as being mathematics. What kind of things do you accept all together as a group? So that when one person says something about, let's say, multiplying, that whatever you said about multiplying, like that you can spread out and use scientific notation to do this. If they say that, then the classroom mathematics practice is that students all together are willing to use that. So classroom mathematics practices is the place that I primarily work, but there have actually been papers written about all of these. The individual perspective is probably what most people are more familiar with and more used to, because for a long time, and even now, we have thought about the way that students learn. And so the three different parts of individual perspective is the student's own beliefs, the student's beliefs about mathematics, and then the understandings or the concepts or the activity that they do in mathematics. So I think when a long time ago, when I first met Chris and we first talked about this particular one, I think he said something about, his goal was to write a paper in every one of these different categories. I think he's probably done it. I haven't done it. I haven't written a paper in all those different categories. But I think that the most interesting part about it is not only are there 6 categories there, but as you see that the lines go across, so they are actually reflexive of each other. So social norms develop and students' beliefs about how they are going to participate in a classroom develops, and those two things are combined together. I see the chat. If you just have to interrupt me, somebody, if you need to. So the interpretive framework, the idea is not that we have to study everything that we study with all 6 pieces. That would be pretty tough. But that each of these places really are venues or places that we could actually study mathematics. For many of us, or for most of us, I suppose, the individual perspective usually involves thinking about things like constructivism or radical constructivism. So students, how they develop inside, what's going on inside. The social perspective often is attached to, but not exactly, not literally, but kind of to Vygotsky, and how Vygotsky thinks about studying learning as a social activity. So when I got to this, it was really an important moment for me, and I'll tell you why. I believe that there was one right and one wrong, yes, so constructivism is the way it has to work, or Vygotsky social culturalism is the way it has to work. I thought all of that. But this says we can study things in all different ways. And so we don't have to just pick one or the other. And that was hugely life-changing for me as far as my career. Let's see. So I did my dissertation on classroom mathematics practices for solving systems of equations. So now I'm going to talk about the 3 different kind of areas that I've worked in over the last 20 years. And I'm going to try to keep a focus on the fact that I think that I've been interested in both the individual perspective, and I've also been interested in the social perspective. So the different studies that have happened, they all can kind of be either be a part of one of those or the other, or sometimes both. So we're going to kind of I'm going to hold myself accountable to thinking that I can tie all my work together. And as you're going to see from the slides and many other people as well, with thinking about the emergent perspective as a good way that we can study learning in mathematics, particularly at the collegiate level. So the first area that I studied, and big surprise, the teaching and learning of differential equations. So, excuse me. Most of you would probably say, if you have heard of me before, you knew I worked with Chris and doing things about the teaching and learning of differential equations. So that was my dissertation, and that's been my work up to, as Chris already mentioned, even as late as 2019 when we published a paper. I'm going to talk a little bit about that work in terms of both the individual and social perspective. So we used a lot of different kinds of research as we were working on the teaching and learning of differential equations, but this was another new thing to think about. Mostly we use qualitative methods, and often we use grounded theory. I have to tell this story because it's one of my very favorite stories. I was working at Valparaiso, and I said that I was going to do my research in use qualitative methods to do my research for my dissertation. And the mathematicians in the department were absolutely floored that somebody who does mathematics, I had a master's in math and I'd always taught math all the way up through abstract algebra, would want to do qualitative methods to do any kind of study. But I believe very strongly that the kind of questions that I am interested in, the kind of questions that I think are, that I can be passionate about, can't be answered with quantitative methods. So another one of the things I learned over the last 20 years is that you have to first choose what you want to study. What is your research question? What is your research goal? What are you thinking about? And as you think about that, then you can choose the methods and the theory that best fit what you're trying to do. That was really different for me, because in general, I thought, okay, I'm going to do radical constructivism. So now I'm going to figure out something to study in that area. I found out that as a mathematics education researcher, I needed to pick what I was passionate about studying and then find the different ways that I could go about it. And I would, for all of you wonderful young researchers out there, I would greatly suggest that you think about that, because that's the way to go. Realistic mathematics education was the curriculum work basis. I'm not going to spend a lot of time talking about realistic mathematics education tonight, just because I only have 45 minutes, but realistic mathematics education was a theory, a curriculum theory developed in the Netherlands. And the primary piece of it that I'm going to talk about or use tonight is called guided reinvention. So in realistic mathematics education, the idea is that as you develop curriculum for teaching mathematics, and this goes from kindergarten up through old age, I guess, the best way to develop the curriculum is to have guided reinvention of the mathematics. So that I like that, because that takes us to what I said was the name of this talk, which is mathematics is human activity. So it's a very different thing to think about than mathematics is what I wrote on a piece of paper, or it's something that was in some guy's head or my professor's head, and I'm just going to have to pull it out and use it. Mathematics is best thought about as human activity. So realistic mathematics education, many of you out there already know a lot of this, but is exactly a good way to do curriculum development if you really want to make mathematics be a human activity versus just a set of theorems, a set of problems, etc. And again, I looked at it from both the individual perspective, and I'll point out which of those I did, and also from the social perspective. I'll point out both. So in the little blue on the bottom left, I'm giving credit to a few people, not nearly all of them that had, because if not, the whole screen would be filled up. But people that I worked with in these areas, very little of the work I did was individual. It was all with a group. So when I say I tonight, I wrote this down to say at the beginning and I forgot. When I say I tonight, I don't really mean I, because it's always been we, and all of the work that I've done is with a we. So here are some of the things that we talked about. First of all, reasoning with rate of change. And this is the one I'm going to talk about. So Chris mentioned this particular one. I put the citation at the bottom: knowing solutions to differential equations with rate of change as a function, waypoints in the journey, and it was in JMB in 2019. It builds on significant work about rate of change in calculus, and I just again I couldn't write down all the number of people that have done work on rate of change. I was smiling because I went to a talk earlier today that was a student talk, or another faculty member talking about rate of change. So it doesn't go away, and it's been studied again and again. And we did all of that work to be sure that we were foundational of that as we build it into differential equations. So rate of change as is seen in differential equations, I guess I should have said that, reasoning with rate of change as it's seen in differential equations. So we studied it both from an individual and social perspective. And some of this work that was done before me, the social classroom mathematical practices and first order differential equations, Chris and Michelle Steffen. The social view, social norms in mathematics classrooms, Erna Yackel, Chris, and Karen King. And then individual, and this is the one that we did at the end: knowing solutions to differential equations with rate of change, or reasoning with rate of change. So I do want to make a mention of the word reasoning. I was at another talk earlier, and I was smiling because certain words like understanding or knowing or reasoning are really pretty hard to define. And so I acknowledge the fact that saying reasoning with rate of change isn't terribly well defined, but I think in some ways it's a little better than saying, do they know it? So I think most of our work, we never really tried to say that students know it. We might say they reasoned about it or their activity showed it or whatever, but we didn't really say we can actually tell if you know it exactly right. So I want to talk a little bit about this paper that we just published in 2019. So I'm going to bring this up. I am relatively sure that the people in the back of the room can't see this, so I'm going to tell you a little bit about it. I'm relatively sure the people who are watching online, however, can see this. So our idea was that the idea of rate of change, or rate, which had been studied at the middle school level, elementary level, high school level for a long time, could be expanded or enlarged possibly into the work in differential equations. So, but on the other hand, we were strong believers that when you learn, or if you learn, I guess you should say, you don't get there by just going in a straight line. I think that many of us, when we started, probably believed that. We thought that first you learn this, and then you learn this, and then you learn this, and then you learn this. And it just doesn't happen that way. So we kind of used an analogy of being in a river, flowing down the river, and that these were places, these are things that would happen as you were progressing down the river. And they wouldn't necessarily happen in exactly the same order or in exactly the time frame or in exactly the same way. But it was just a stopping spot as you're going along, as you work on developing reasoning with rate of change in differential equations, or at the differential equations. So I'm going to read across the top, student reasoning with rate of change. Again, if you're in the ballroom, I don't know if you can see this or not, so I apologize if the back. So the first waypoint was reasoning with rate of change as a constant slope function. So I have to tell this story because it's another one of the favorite moments of my life. The first time I gave a poster when I was still a doctoral student, I did a paper on rate of change in differential equations. And I had a mathematician come up to me and say, why are you saying that? Rate of change doesn't have anything to do with differential equations. They're not connected at all. And I was pretty much astounded, but not only was I astounded, I was determined to make a difference, because I believe that rate of change is what differential equations is all about. So we started this work, as Chris said, a long time ago. We finally finished it in 2019. This is the different ways that we found, and it didn't happen one day. So you know how most of us, particularly those of us doing dissertations, and a lot of you out there are doing this at this time, you have one project and you have one or two research questions and you develop that all. What this paper came out of is not that way at all. It was over 20 years. I shouldn't say over 20 years. It was looked at and studied during the course of 20 years. So these things, we have examples of these all in many different places, in many different research projects, in many different classroom experiments, all the way across. So we reasoned that slope, it can be seen as a non-changing output value. So for instance, f of x equal 2, that would be an example of slope as a constant function. So when students, we have several examples of when you ask students about how a solution may be going to progress, they'll say, well, the slope is 2, and therefore it's going to be a straight line. And so that's why we call it constant non-changing value. The second one says that the waypoint is as a ratio of discretely changing input-output values. So this didn't come as a big surprise, because there's also considerable research about the idea of looking at things kind of not chunked up, but in intervals. And so this discretely changing ratio function is how students can think about a solution. In a solution, first you go a little bit on a little straight line, and then a little bit on a straight line, and a little bit on a straight line, and a little bit on a straight line, and then continue like that. So that's the second way that we found that students, when we're asking them to think about how are these solutions going to come about? They thought about them as discrete units of different lines kind of connecting together. The third one says, as you can see, time invariant function. The reason it's in red is not because it's special, but because I'm going to give an example of it here in a minute. So that's why it's in red. As a value that does not vary as time changes, which indicates the time invariance behavior of solutions. Whoa, that's a lot of words. So that indicates that the solutions, if it's a differential equations where you have a function as a differential equation that's autonomous, it will not vary as time changes. So as you go across, the solutions look the same all the way across. And I'm going to give you an example of that one because I think that one's a little harder to understand. The fourth one is an object that indicates the behavior of all solutions. So you're thinking about this differential equation, and it's an object that not only indicates one solution, but by knowing this differential equation, you can, and those of you who teach differential equations know this, you can go to many different starting spots or initial values. But if you have an autonomous differential equation at all of these different values, if they're horizontal, is autonomous, they will go across horizontally. And finally, as a parameterized function. So as an object that indicates the behavior of the family of solutions. So this is, if you're not a differential equations person, I don't want to spend a whole lot of time on this, but I think it shows how our work has kind of developed that instead of thinking of rate of change just as a slope, which is what it was up to this point, the idea of the functional rate of change, which in this case means is a differential equation, can give us a whole lot of information that it kind of progresses. I would say it doesn't necessarily progress exactly like this, but generally it does. And if you were going to play devil's advocate, you probably would suggest that this all happened this way because that's the way the curriculum was developed as well. And I have to give a nod to that as well. That's a possibility. Okay, so we're going to look back at the waypoint. So, oh dear. Oh yeah. Okay, so waypoint 3, look at how rate is invariant. I wanted to show an example of that, and I'm guessing this is not going to happen. So I think you're going to be able to see this video, but you're not going to be able to hear it. That's my guess. So I'm going to be John. So John was asked to go to the board and explain it about what happens when you look at a differential equation solution, which you can see there is in the green. And then what do you know about the solution that starts at the other dot that's up there on the top? So this is one of the tools of the trade that we use when we were teaching differential equations, or when we are. He actually had a transparency. So he put the graph on the transparency, the solution graph, and then he showed how you can just invariant, the solution curve is invariant as far as the shape of it, and it doesn't matter where you start as far as time goes, but that it works across all the way. So that's his example, an example of how that's what we mean by we say that the slope is invariant over time. Okay. The second one is the waypoint number 5. Oops. And I wanted to remind you what that says. As a parameterized object that indicates the behavior of the family of solutions. So I put in a couple of pictures to show that a lot of the work that we have done includes things like gesturing. I'm not going to talk about our work in gesturing tonight, but here's an example of gestures. So we have a student that's standing up and they're showing about the solution space. So in differential equations, not only can you find a solution, but all of the solutions together make what we call a solution space. So the young woman there is showing how things change up and down as an example of how it not only shows you about differential equation solutions, but how the spaces of solutions change. And then the person on the right has a picture that he's showing, and he's got his fingers out and he's showing about how those different solutions, the different solution spaces change as a parameter changes. So that kind, I don't have, again, each of these could be a whole hour talk. So that's where I'm going to go with that. So I was thinking about, is that about individual in the individual, or is that about the social learning? And I think it's kind of halfway in between, primarily because all of the work was done in classrooms that were differential equations classrooms. But the next one, which is I'm going to call dynamic reasoning, is pretty much individual. And this was my dissertation work. And it's individual in that I actually pretty much studied two students, or several students, but I studied two particularly that I focused on and looked at how they reasoned in these problems. So dynamic reasoning is developing and using conceptualizations about time as a dynamic quantity that implicitly or explicitly coordinates with other quantities to understand and solve problems. So at some point, I should mention that most of the work that we have done in the differential equations, not all of it, because it does expand some, but a significant piece of it involves time. And there was a question earlier today, someone asked in one of the talks about, or put it in the chat about, thought it was interesting because actually reasoning about differential equations in terms of time, I think has been found to maybe be easier or more reasonable for students to reason about than if the dependent variable is not time, like if it's volume or height or something else like that. But for my dissertation, or for this particular piece of the talk, I'm going to talk about time as being the independent variable in the differential equations. So I found that there are five characteristics of dynamic reasoning. Making time an explicit quantity. So because we're working primarily with autonomous differential equations during most of the work that we were doing, one of the things that became important is that when students are learning differential equations, they need to be able to kind of pull out the notion of time and think about things in terms of time, even though they're not, even though the dy dx or the dy dt might say 2y minus 3y squared. But there's no y in the function. I mean, I'm sorry, there's no t in the function, but yet t is part of it. So students have to be able to pull out and understand and think about using time as an explicit quantity. And they use intuition from real life that time never stops. This is kind of what we believe, and it makes it, I can remember several times when I would say to my students, can time go backward? That's a question. And the answer, it depends on who you're talking to and how you're talking to it. But we tend to ask students to think about what would have happened before time zero. So often the students will say time never stops forward and time never stops backwards. Although again, I think we could argue that a little bit. Using both quantitative and qualitative reasoning. So in other words, when they're asked to speak about or talk about these things, they might talk about it qualitatively, like, I think it's just getting bigger and bigger. That would be a qualitative reasoning, or a quantitative reasoning might be, I see that for every time time goes one more second, then the height changes by 2. So that would be quantitative reasoning, and the other one is qualitative. And we found that students intermix and go back and forth between those two different things. And that's one way that they can better reason about solving differential equations. Finally, discrete and continuous, I'm going to leave that one, and I'm going to go to imagining the motion. So I think this was my favorite one, because imagining the motion means that students are pulling on things that they know, things that they can have based on to do this work. So three-dimensional spatial visualization, the fictive motion metaphor, and the fusion of context and representation were the three kinds of reasoning that we found for imagining the motion. So this is a quick example of imagining the motion three-dimensional visualization. So here's a problem. The following is a sketch of x versus y that is produced over time. Those of you who teach differential equations, you can see that this comes from a graph of a solution in a phase plane. Look at each of the following suggested systems of differential equations and decide if any of the choices could describe the graph. So I wish we had time, but I'm not going to ask you to solve this or do this work ahead. So you're going to get to know before. This is what Brandon says. And I'm going to read only the red because that's the part that I wanted to bring out. The picture on the left is actually Brandon and the professor doing this. Again, I was pretty leery of doing any kind of video. Let's say it starts down here on this side of the line. It's coming up and moving along T, and then it swings out this way right here. Then it's moving along T, moving along the line. I think you also have to see some vectors out here because it is off of the line. And he's standing at the board and he's actually physically having it come out into space from him. So he's describing it in a three-dimensional way. Fictive motion metaphor. So this has been around for a while. The idea is that we talk about graphing and we talk about functions actually as being in motion. So we say it's going to go as time passes, the solution increases exponentially. As R goes up, the rate of change goes down. These are examples of the fictive motion metaphor. And it's kind of interesting because I think we all use this pretty much regularly. But if you really pause to think about it, a function, as you think about it, is a set of points. And the set of points, in many cases, as you know, have graphs, and the graphs might look in a certain different ways. But the function itself doesn't actually really move. The function itself is actually is nothing more than a set, probably often an infinite set of points. So, but people really, it really helps them to think about how think of a function as moving to make sense of some of the problems. So here's another one of this, and this is from the same example, different student. Look, when time increases at the same amount of time, yeah, but this is going to get bigger and bigger. So it's going to start getting bigger. What does he mean by it's going to get bigger? What is going to get bigger? Well, he means that as the X values increase, the Y values are increasing as well. But again, that isn't exactly true because the function is the function, but that's how he made sense of this problem. On down to the next red. Otherwise, it wouldn't be a straight line solution because if it slowed down, it would have to slow down to a point and then reverse the other direction. So it would run into a different equilibrium point. So it's like this function is a car or an object or a mouse running around, and it's running all over places, and that's how he made sense of the problem. So that was about an individual thought process about, that was an individual thought process about how students make sense of differential equations, and particularly the solutions to differential equations. So that kind of is a quick broad overview of how we look at both individual and social construction of meaning in classrooms, particularly in differential equations. So the second part of my kind of career involved something slightly different, supporting instructors in implementation of the curriculum. And this was an NSF grant. We had a collaborative grant, Astray and Christy and I. And those are the grant numbers. And so I'm going to talk a little bit about this because I believe this also still fits in the same category of thinking about things in terms of individuals and thinking about things in terms of the social and how those go together. So I'm going to give you a little background in this particular grant, we call TIMES, Teaching Inquiry-Oriented Mathematics, Establishing Supports. We studied 3 different supports: curriculum materials, summer workshops, and online work groups. So I'm going to mention a little bit about each of them. The curriculum materials I've talked a little bit about before. We use the instructional design theory of realistic mathematics education, and students reinvent the math through participation in the class. Their mathematical activity builds from starting points that are meaningful to them. And then the procedures emerge from the concepts. And all of them, analytical, graphical, and numerical methods, are all kind of taught simultaneously. So this is a very different view of the way that the differential equations had been taught than before. Now, this is much more common today. So I haven't taught from any new books lately. So I'm sure that this is more common. But back then, in 2000, when we started, when Chris started, and then I joined him, differential equations was a set of recipes. If you see a problem that looks, this differential equation looks like this, you solve it like this. If it looks like this, you solve it like this. And at the end, you have a list of different differential equation recipes to follow. So we developed a set of materials that were very different than that. We called them inquiry oriented. And in these materials, the students reinvent or use mathematical activity to make sense of the mathematics and build it. So again, we're talking about mathematics as human activity. I really particularly like the last point, which is procedures emerge from the concepts, analytical, graphical, and numerical. So I thought I would give one quick example, not enough time to, not enough time to give hardly any example. Okay, I'm gonna, give this example, then I'll go on. A crop duster with 2-blade propeller is rolling along a runway. On the end of one of the propeller blades, which are rotating clockwise at a slow constant speed, is a noticeable red mark. Imagine that the propeller leaves a trace in the air as the plane makes its way along the runway. So the students are supposed to think about what it would look like if a trace of red at the end of one of the propeller blades, what it would look like as they viewed it from different perspectives. So the reason that I bring this one up, one is that it involves students being actively, physically involved in something. And we tried very hard to include embodiment into the curriculum materials. And I've lost the second one, but that we liked it because of that. And because for me, the first time I ever did this, it was again, one of those aha moments, because it turns out that the behavior that you might see with that trace is what a 3-dimensional solution to a system of equations looks like. So this is the introduction that we give our students to a system of different solutions to systems of differential equations. And I'm looking at the time saying I'm not going to have to, I was going to have you all try it, but I'm sorry about that. I'm going to stop because I want to give you a chance for some questions. So this is just one of the many tasks that are in the entire set of 1 semester curricular materials. And that was one of the supports that the grant was going to use. In abstract algebra and in linear algebra, they also had a set of materials that were very similar to this, developed in the same ways, and they were studying that. And my piece was to study the differential equation implementation. We did summer workshops. And again, time doesn't allow me to talk about that, but I'm going to go on and talk about online work groups. So we did a lot of research in times, implementation over time, and that was the individual. Diversity and equity in classrooms. We published several things about that, and I don't take credit. I was along for the ride and I loved it, but I haven't been the primary on most of that work. And then the online work groups as professional development is where I kind of focused. So quick context, I want to talk a little bit about these online work groups. They were innovative. We used the idea of lesson study across faculty that were geographically spread out. So we found that we were going to ask these faculty members, use our materials. They're really good and we love them, and you've never seen them before and you've never done anything like this before, and you just go out and do it. Well, obviously, as you can probably guess, I hope some of you are smiling, that's tough. And there's been, so as many of you who are sitting out there are doing the research, know that's a tough place to go. So what we did is we developed what we called online work groups. And so we got people from all over the country who were willing to come and attend in a virtual setting, the regular 1 semester, every week meetings to discuss how they implemented and what they learned from the materials. So it was a big deal for those people because they had to commit to coming in once a week. So we were interested in, we had many of these work groups, differential equation work groups, linear algebra work groups, abstract algebra, and we studied about how that implementation looked. So sometimes we looked at the individuals and how it was connecting from their individuals to out to their individual participation in the work group affected the way they taught. And sometimes we just studied what it looked like in there. So I was one of the teachers. And I had two colleagues that worked with me on this, Nick Fortune and Will Hall. So this is what we found out. We found out that you could actually determine what it looks like. I'm checking time again. Yeah. What it looks like as you worked in being a part of an online work group. So we've been publishing, and we are having a paper soon. Oh, shoot. About this. So as you can see, this is the different actions that an instructor or that the facilitator took. We never called it instructor or leader, but facilitator, which is they gathered information, they verified information, they contributed their own information, and they supported the group as well as progressing the session forward. So we found that the online work groups could be considered both as individual, because each of these people went out and did their own thing, but it also could be a social group because we studied how they cooperated and worked with each other. Okay, so the grant ended and I went to NSF, and then after I got out, sounds like I was, yeah. After I finished my time at NSF, I started a job as department chair at Embry-Riddle University. So I thought it's really interesting because not all of them, but I think it's 95% of the classes are online. And out of all of those, that 95%, 90% of them are asynchronous. So I'm like, how are we gonna do this? What does this mean to think about the social construct of a meeting when every student is doing something on their own out in another place? And so that's what we've been thinking about, and that's what we've started. And this is only a very preliminary work. If any of you know Daryl or Zach or Derek, I encourage you to ask them a little bit more about what we've been doing, because I'm not going to have time to talk a lot about it. So this is what I found. There's not a whole lot of research about how do students socially construct meaning, or together construct meaning in an online asynchronous setting. We all know because of COVID what it was like to teach online, but at least the courses that I taught online, they were all synchronous. So yes, there was a whole lot of technology involved with having to figure out ways to put in groups and share things out and all of that, but you were still together making meaning about differential equations or abstract algebra or whatever calculus, pre-calculus algebra. But what if you're asynchronous and you never meet the students, they never meet each other, and they're never online at the very same time? What do we know about how that can work? So this is a new perspective on this. We know that online courses have become ubiquitous. They're everywhere, and I don't believe they're going to go away, although maybe I'd love to have somebody argue with me that they're going to go away. I don't know, but I don't think so. So my question is, where does this fit in the emergent perspective? Is it psychological or is it social? And my answer is it's both, and that if we work on it, we can make it become more than just one individual constructing and doing problem sets and taking tests and doing quizzes in their own little room. So I'm working with two colleagues to bring together research from inside and outside math education to make sense of how students can learn in an asynchronous online setting. Oh gosh, I lost this. So I'm going to name them out since I lost them. So the two folks that I'm working with now are Daryl Chamberlain and Zach Reed. So this is what we thought. Classroom discourse is a fundamental activity. Students have an opportunity to gain mathematical knowledge. We want to see what it looks like. So these are the research questions that we're working on, and I'm going to let you read them. As a quick aside, because I think it's interesting, the folks our students are quite different than most traditional students are. And again, I don't know if you can read this in the back of the room, but we have 75% undergraduates, 73% part-time, 82% of our students are age 25 and older, 60% of our students are active military, 24% of our students are veterans, And most of them are male, although we're working on that right now. So it is a very different environment for these students. Almost all of them are full-time, working full-time, many of them in the military. So we're coming at it from a very different perspective, because those students, how they think about and see things, first of all, they're at least 25 years old, so they're adults, fully grown with families often. And so I think one of the big questions that we're going to eventually get to is, how does that affect the way that they participate in these classrooms? So we have three kind of pieces that we're bringing together to do this work. So the first one is called the Argumentative Knowledge Construction Framework. And it's a framework to analyze argumentative knowledge construction in computer-supported collaborative learning. So this is the word argumentative here means argument, not argumentative like arguing or fighting or disagreeing, but argumentative as in developing and bringing forward arguments. So this, Weinberger and Fisher developed this framework to support this, and they studied online learning in this situation. And so we took that framework. We also took Toulmin's framework, and many of you know about that, which is about claims and warrants and backing. And then we took all the research about calculus, because we started our research in the calculus realm. We would have to go through this again if we move to another area. And we put together a framework that we think will be useful, and we're still just working on it to look at this framework, to look at this social learning in calculus, online, asynchronous. So we have the argumentation. Our codes are that students will make an argument, a counter argument. They will integrate what they already know into their work. They will just have non-argumentative moves that don't mean anything. And then we use Toulmin's scheme to look at backing and warrants and data. And so the DQC, which is across the middle there, is they take data and they make my mind went blank, Q, and then they make a claim. So question, and then they make a claim. And that comes from Toulmin. And then we looked at prompt specific understandings of the derivative and composition or whatever we happen to be working on right now. So here is the epistemic. And then we're looking at the participation on how often they participate and how they're more heterogeneous or homogeneous in the kinds of claims and arguments that they make. So we're taking this and then we're analyzing online work. So we have very few results yet, but I think that we're going to find some interesting thing that's going to allow us to make some differences in the way that online asynchronous classes are taught. So first of all, the tasks matter, big surprise. It turns out that if you don't ask the kind of tasks that allow this kind of argument, counter argument, and integration, then you can't really study that. If you ask a question, and I was at an earlier talk where somebody said, if you tell the students to reply to something that a solution, and the student reply, that was really pretty, I like the color of your pen that you used on that, that probably isn't going to further the social mathematical construction of meaning. So the tasks are important, and how you have the students are. Students can integrate and provide counter arguments in this environment. And number three, I think, is the most important thing we found so far. Without some help, it is not common for students to use argumentation and to develop these new understandings in an asynchronous manner. So we're looking at ways to enhance our online courses so that students learn about what it's like to prepare an argument, they learn what it's like to give a counter argument or an integration, or to not do that. And so we're going to try to study that. And again, this is a case where we are looking at how students are constructing meaning together, the social side of learning, but we can also study how well the students do as individuals, and then we can reflexively connect the two. So it's kind of exciting where we are going with this using the realistic mathematics ideas of guided reinvention. So that's it. I said I was only going to talk 45 minutes, and I've talked almost an hour, so I'll go through this quickly. But this is just kind of me sharing with you what 20 years has brought. There's not one right way to do mathematics education, big surprise. The study of learning and teaching mathematics needs to be both from cognition and from the interactive social perspective. And mathematics education can continue to live in the non-technology world, but technology has changed the world and its teaching, and we can't just forget about it. It's going to be there. So we need to be sure to allow for that in the work that we do. Students' intuition and prior knowledge can support new learning. Often this is better when not in the symbolic. So when we talk about students' intuition and prior knowledge, and you give them a function or a formula, that doesn't always work as well. So we often need to look at the graphical and numerical representations and tie it back together. And I already told you this: be passionate about what you study, choose your question, then your method. Educational research is best done together. I can't thank enough all of my many colleagues that I have worked with over the years, and how they have been supportive, and they've probably come up with all of the ideas, and I just maybe went along for the ride. And that's it. Okay. So it's 8 o'clock. I stopped at 8, but I think we have 15 minutes for some questions. Whoever is moderating this, do you want me to quit sharing my screen?
Yeah, I think that'd be great, Karen.
Yeah, okay.
So, again, in the spirit of the conference, we're going to try an experiment with questions in the room, in person, but also on chat or virtually. And I've been sending some directions to the virtual participants. But I'll start off with a question in the chat from the virtual participant. Aida wants to know, and I think, Karen, you can see this in the chat, but the question is, for the benefit of everybody in the room, in your current study, when you are designing, quote, discussion activities, what kinds of platforms are you utilizing? Discussion boards, Perusall? Do you see any limitations and affordances of different platforms for engaging active participation in an asynchronous format?
Okay, how many questions was that? So currently we use discussion boards, and Zach is working on developing what we call conceptual quizzes, where he gives a short video lecture, and then the students actually are asked questions about that video lecture at the same time, that are not graded, so that they can listen to somebody talk and then give it. But mostly the discussion boards is where we have been looking at our work as well. We have Perusall, but we don't use that currently in any of our mathematics classes. We also are beginning to use something called Yellow Dig, which is a framework similar to like Facebook or Twitter, that students would use, but where they could actually bring questions and students could talk back and forth between them. Again, I think though that the issue is in any of these situations, the students are not used to learning, not used to doing online learning, where they are really expected to make sense of someone else's work. That's the issue. They're not used to they can't make sense of someone else's work because they've never been asked to do that before. So we're really working on some materials and some things that will be helpful to that maybe students will learn more about that. They're used to probably making comments like that in a history or an English class, but in a math class, very rarely were they asked to read somebody's argument and make a decision on whether it's right or wrong, and then comment and make a new argument to go with that. So that's been really hard. The materials that we use, by the way, are traditional. The students have an ebook that they use, and then Zach has been adding in a whole lot of other things as well to kind of complement that. Oh, and then the other question was about issues. Well, we have a lot of issues because I just told you what kind of students we have. They're almost all over 25, and many of them are in the military or veterans, and so they could be around the world. Sometimes this week, for instance, I got an email that said the folks from such and such of an Army or Navy base are all of a sudden not going to be in their classes anymore because they were just deployed to Europe. And so there are a lot of issues with working anything online like that. But if that's not an issue, I would still go back to the other, which is they don't know how to talk verbally. I mean, they don't know how to type and talk about mathematics other than just, here's how you do a problem. So we're working on that. Okay.
Any questions
others?
in the room, or a follow-up in the chat, or anybody? Oh, we have one in the room. Sam will be running around with the mic. Megan,
Is it on? Yes. Okay. Megan Nuero here. Thanks, Karen, for the good talk. I want to start with a little story that 15 years ago, 2007 was my first RUME, and I was getting a master's, and I didn't know what a PhD was, and so I decided to go to RUME, and the first person I saw was Karen, and so I think her kindness you all can see tonight, and so I'm glad you were able to share that with me, and it's been nice to see that over the last 15 years.
Thank you, Megan.
Okay, so my question was actually about your last slide. I think maybe you already told us, but my question was going to be if you have any advice, since you did a nice job kind of talking about 20 years of work, if over those 20 years you have certain pieces of advice you would like to offer. It could be to grad students, early career faculty, mid-career people getting ready to change the direction of their career, but any kind of advice that you've thought about over the last 20 years.
I haven't been thinking much at all, but I'll make up something now as we go. No, joke. I think the one thing that I said that I would still go with is find what you are passionate about, what you really care about learning about, and then go find the right methods and the right theories to go with that, because there is no one right theory. There is no one right method. You might be told that by other people, but if so, come back to me, because I will tell you that there is not. So to find what you're passionate about, because particularly dissertations, you have to look at that data for a very long time. So you really want to find something that you can be work about. Secondly, work with somebody. As you could tell from the many different places, I've had lots of communities of folks that I've worked with, and you don't really know which of those ideas were yours and which they were each other's, but finding people to work with, it doesn't have to be somebody at your own college. It could be somebody wherever else you are. Chris often tells the story of one of his colleagues that was interviewing for a job, and that person met him, and they didn't get the job, but they ended up collaborating on it for a very long time. So find collaborators wherever you can, and don't hesitate to keep working on that. And then finally, and I guess this is what we all struggle with, you still have to have a life. So yes, it's really important to understand about how students learn differential equations. Well, absolutely, I loved it, every minute of it. But while I was doing all that, I had 3 teenage boys, and I still managed to go to football games on Friday night and see all 3 of them get married, and I part of a faith community. So please don't. I actually had a student, 2 students actually, that said that some of my first 2 graduate students who said, "We're not sure we want to do this, Dr. Keene, because this is all you do. Your life is here, and we want to have a life outside of that." And that really got me. So I changed. I said, okay, they're right. This is a hugely important job, but I also have a life. So I would say keep a life. And I think one more thing I thought of, and then I'll be quiet, which is that everybody has to find their own niche. So some of us are researchers, some of us are practitioners, some of us are both, some of us are administrators. And so find whatever makes you happy. There is not one wrong or right way to be a mathematics educator. Okay, I guess that's the end.
Want to quickly give Igor on virtually a chance. He's raised his hand. And Igor, if you can unmute and just ask your question.
I see you,
Thank
Igor.
you.
Hi.
Hi, thank you so much, Karen, for your lovely talk. Really enjoyed it. I would like to follow on one point that you said about finding the right theory and finding the right method. So if I remember correctly, when computers became more widespread and they entered the classrooms, people started talking about epistemological shift in how we think about math and how we think about teaching and learning of math. When the online learning became more widespread and now forced on all of us, so a kind of similar claim was made by people who were actually in this space already. I'm fascinated by the context that you described when the online learning is not synchronous, which is a kind of very heavy assumption in this regard. I wonder about your thoughts. Do we need a radical shift in the way we think about math and math teaching that should take us forward? And do we have theories and methods that can support us already in this journey? Thanks.
Well, I'm glad you didn't ask me a hard question. I think that as we have talked about it, this is we, I'm talking about Zach and Daryl and I have talked about it. We don't think about it maybe being a big shift as far as epistemical, I can't get the right word out, in an epistemic way. But I think that one of the things that we've really kind of promoted or thought about is something that has already happened and that I will bring up, which is that thinking about mathematics as not just being a set of problems to solve that are routine and rote problems that your teacher showed you first and then you go do it. So the great majority of students, even today, after all the work that we have done, they still believe that. And so I would suggest that making this shift to online, particularly asynchronous learning, we're going to make it be worthwhile and not just be a set of students following a set of problems and doing them until they get them right. We have to start thinking more about the concepts, the conceptual meanings, and the discussion of the words that we use being able to be put on paper, or in this case on computers, so that epistemically we think about not only how do you do a problem, but what does it mean to do a problem? When do you do the problem? And what does it mean after you get the solution to that problem? So I believe it has to do with changing from the standard procedure type thing to others. And I do want to say one thing, Igor, what was your name? You took, your thing went away. Yes, my work hasn't gone, the very little proof has been a part of my work. I mean, there's some proof in differential equations, there's some proof in calculus. So that might not be the same if we went to abstract algebra and linear algebra, and those areas. So I couldn't say about those. Okay.
We'll take one more question. Vilma in the room here.
Where is the camera? Hi, Karen. My name is Vilma. My name is Vilma Mesa. My question is, I think it's a follow-up from Igor's question in terms of methodology. So you said that you like qualitative work and grounded theory, et cetera, et cetera. My question is, given the status of, the possibility that we have now to do large-scale qualitative analysis, how do you see your work evolving in that way? Or have you thought about the possibility of also doing quantitative work?
Mm-hmm. That's a really good question. The answer is that I believe for me, primarily, I don't know if that's something that I would be passionate about, using big data to do qualitative or quantitative work. But I do believe that, at least in our world at this point, being able to take things that we learn qualitatively, for instance, and then being able to introduce those into classrooms or students or student work or whatever, and having large-scale studies that show that this kind of thing is actually effective in a quantitative way is really important as well. So I don't know if I see myself doing very much quantitative work, but I do think that it is absolutely imperative that we do include, and many of you, I don't know how many, but most of you or many of you have done mixed method studies where you do a little bit of both. But I think even just taking things that we know and learn from a quantitative perspective and then studying the why from a qualitative perspective, or vice versa, taking what we learn qualitatively and then going to do large scale studies, absolutely imperative in this particular day and age. And of course, we didn't used to be able to do that, right? So this is another place where Igor says, technology allows us to do the big data study. So absolutely, I think that that's really important.
So thank you, Karen. And I'm hoping that we can sort of clap loudly enough to let her know how appreciative we are in Florida.
I hear you. Thank you. Thank you all. I love you, RUME. I do.
I'm thankful to everybody for allowing today to happen. We get to do this all over again tomorrow, and hopefully we'll have just as much fun. Sam has a couple of quick announcements.